Welcome to Lecture 7 of Introduction to Computer Architecture. I'm Simon Moore, and today I'm going to tell you more about processor pipelines. Let's review the sequential pipeline that we were using in the last lecture. So here I've just got the data path components, and we can see that we've got a sort of instruction fetch phase where we fetch the instruction from the instruction memory with the program counter provided by the branch unit. We then move into the decode / register fetch stage where we decode the immediate, we decode the instruction, although I'm not showing the control logic here. We fetch the registers we need. We then move into the execute phase where we do the arithmetic operation. And we'll see later, we'll also typically be doing handling conditional branches here. Then we move into the memory access phase, and then finally we write back the result to the destination register. Now we're going to be using D flip-flops to control the flow of information down the pipeline in lockstep with the clock. You remember the D flip-flop symbol from Lecture 2 and also, of course, from your use in 1A Digital Electronics. Just a reminder that this has a data input, D, a data output called Q. There's usually a reset signal, though I've not drawn a wire going to it, and a clock signal. And the principal operation of this is on the edge of the clock, quite often the rising edge of the clock. The data is basically copied from input to output, and when we don't have the rising edge, then the flip-flop remembers the output state, so no matter what happens with the data input, the output doesn't change. And this allows us to sequence data through our circuits. I'm going to abstract the D flip-flop to the following simple diagram where D is on the left and Q is on the right, and moreover that black block is typically going to represent a whole bank of D flip-flops. So we'll have one D flip-flop per bit of data or even control signal. And the clock and reset need to be connected, but I'm not going to draw them on the diagrams because it will just make the diagrams very complicated. But whenever you see one of these blocks, assume there is a clock tree that's driving all the clock inputs, and that there will be a reset network so that we can reset the design. So if we then use these banks of D flip-flops, we can use them to form a 5-stage pipeline. And note here that we've got 5 banks of D flip-flops in sequence, and therefore this is a 5-stage pipeline. It's perhaps easiest to think of the D flip-flop being at the beginning of each stage in the pipeline. So instruction fetch begins by fetching the instruction from memory. And we then move on to decode, execute, memory access, and finally write back. I suppose I should have drawn the box, the write back box, starting at the last D flip-flop, but it just wasn't quite space. So I hope you'll forgive me. So let's think about the pipelining operation. First, we'll look at executing one instruction at a time, like an assembly line where you complete manufacture of one item before you start on the next. Then we'll look at the pipelining operation, and so we want to keep fetching instructions, so we fetch an instruction every cycle whenever possible, while in parallel we do decode, execute, memory access and write back stages for other instructions in our assembly line or in our pipeline. And the objective here is to try to fetch a new instruction every clock cycle, to try to keep all stages of the pipeline busy. But also, very, very critically, we have to preserve the programmer's model of sequential execution. Okay, and that is a little bit of a challenge, and that is going to cause things to slow down, but it is necessary to build a processor that people can easily program against. Also, people have in previous processor architectures with different instruction sets sometimes to expose some of the pipelining behavior to the programmer or to the compiler. But the problem then is you're often locked into a particular implementation of the processor. So I think really the community has concluded it's better to not expose any pipelining behavior at the hardware-software interface, and to stick with a simple sequential model, even though that does have its limitations. So let's look at actually operating a load instruction, or in fact load and store, because they sort of exercise a lot of the pipeline. So first, obviously, we fetch the load or store instruction from memory in instruction fetch. And here you'll notice that I've indicated on the D flip-flops that I've sort of split them in half, if you like. So the half that we're kind of using for this step is where the address is being provided by the leftmost D flip-flop, and then the result will go into the next D flip-flop on the next rising edge of the clock. Then at the next clock fetch, we fetch the registers and decode the immediate and do any other instruction decoding for the control logic, and that then gets latched. And on the next clock cycle, we will perform the ALU operation, do the execute, and for a load or a store, we'll of course do an address calculation here where we're adding the RS1 value to an immediate. Then we conduct the memory access. So in the case of a store, it writes the RS2 value to memory, and that's been sent through. If it's a load, then it reads data from that computed address, and of course we'll ignore the ALU result that sort of goes over the top of the memory block, and we will feed the loaded data through to write back. And in the write back stage, we just write back the load. However, one thing to note here is what happened with that RD control signal. Remember, we want to start executing lots of instructions going down this pipeline, and if we're not careful, that RD signal will be for a different instruction. In fact, this applies to all instructions that are going down the pipeline. I'm just happen to be illustrating it using load. So to fix this problem, we want to propagate the control information down the data path, so along with the data path. So in other words, the RD signal, when we decode it, rather than feeding it into the register file, we're going to feed it into the pipeline latches, and that's going to propagate all the way down the pipeline until it gets to the write back stage, and at that point we're going to send the RD value to the register file along with the write back data, so that the data and the place in the register file where that data should be written arrives at the same time. So more generally, we're going to get the control signals to flow with the data path. And you remember last lecture that I talked about the various control signals. So, controls for the multiplexers, what the ALU operation is, whether the data memory does a read or a write, or whether we don't use it at all, and so on. You'll also notice in this diagram that I'm feeding the control signals for the branch unit from the execute stage, okay? Because for things like conditional branches, we need to use the ALU to compare register values, and we've got the flags, 0 and sign, that get sent over to the branch unit, and we'll also send the branch type information at that time, and we'll also, you'll see, going to send the jump offset, so that basically all the control information and that immediate value arrive at the branch unit at the same time. So we talked briefly last lecture about hazards, and let's look in more detail. So just a reminder, the challenge here is that we want to preserve the illusion of a sequential programming model, but we want to run the code as fast as we can. So the hazards, if you like, the problems exhibited by our pipeline are data hazards, so the risk of stale data being used, and control hazards, i.e. we fetch the wrong instructions and start executing them. To illustrate these issues, we're going to abstract the pipeline to the following diagram, and here I've got sort of little pipeline latches indicated, and we've got our blocks: instruction fetch, decode, register fetch, execute, memory access, and write back. So let's first look at load-to-use dependencies, which I introduced last lecture. So here I've just abstracted it to a very simple example where we've got a load word that loads a value and puts it into register T2, and then we're going to add that value to T3. So we've obviously got a load-to-use dependency on register T2. Now let's look to see how these instructions, so the load instruction I'm going to just refer to as L and the add instruction as A, let's see how these progress down the pipeline. So we're going to look over time to see what happens. So at time step 0, we'll fetch the load instruction, the instruction fetch. That will then propagate to decode, and whilst we're decoding load, the add instruction is already being fetched. Then in the next clock tick, everything progresses down the pipeline, so the load will hit the execute stage, and we'll start doing the address calculation. Now, of course, we haven't actually done memory access at this point, and so the add instruction, which is currently in decode and register fetch, if we provided add with the current value of T2 that's in the register file, it would be a stale value. Okay, so we're going to have to stall add in decode until the result has been written back to the register file. So in the next cycle, load is going to proceed down the pipeline to memory access, but add is going to stall in decode. We're then going to allow load to get all the way down to write back, and at this point that result from L will be written to T2 and available for the add instruction. And so on the next clock cycle, add can proceed to execute, and then it will proceed down the pipeline until it's written its result back. So clearly here we've got two bubbles appearing in the pipeline, and this will slow us down. So we would like to do better. And last lecture I talked a little bit about forwarding, and we're going to see how to do that at more of a hardware level. So we want to try and remove pipeline bubbles using forwarding. So we want to remove as many pipeline bubbles as possible to speed things up. The approach is to forward results from the producer pipeline stage to the consumer stage. And as I said, this is called forwarding. So let's look at forwarding the result from the load instruction. So obviously we don't actually have the result until we've performed the data memory access, and in fact that data memory access typically takes quite a lot of time, so it's really only once we've got the result in that write back latch that we can do anything with it. However, what we can do is when we're writing the value back to the register file, we can also forward that value via some multiplexers into the ALU, and in other words we can provide the value one clock cycle earlier. So let's look at the implications of this on our load-to-use dependency hazard. So exactly the same problem as before, we've got a dependency on T2. So as before, over time we're going to fetch the load instruction, that proceeds down the pipeline. We also fetch add, and they proceed down the pipeline together until we get to this point, at which point we still haven't actually managed to load the new value. So we've still got to stall A. We can't get around that. So we introduce one bubble in the pipeline as the load has to hit memory access, and once we know that the load is going to hit write back, we know that we can forward the value from the load to the add instruction. So we allow add to proceed to execute. So at this point the add's actually got the wrong value of T2, except we're going to forward the correct value and ensure that those new forwarding multiplexers, which appeared in red on the previous slide, pick up the new value and effectively discarding the T2 value that was read from the register file. So therefore A gets the correct T2 value and can proceed down the pipeline. So forwarding in this instance removes one of the two bubbles, so it saves one clock cycle, but we just cannot remove both bubbles because it just takes time to do that memory access, and there's just no way around that. So let's think about generalizing the load-to-use hazard and how we can avoid it. There's always a load-to-use hazard on any processor, and it's often presented to programmers and compiler writers as a load delay slot, and more complex high-performance processors typically have a more complex pipeline, and they even pipeline the data memory access, so it may well take 3 clock cycles to read that data value. So in other words, we have a big load delay slot in the abstract. And we looked at last lecture at load hoisting, with the aim was to issue load instructions as early as possible and basically try and ensure that there are other instructions between the load and where the data from that load will get used. Now let's look at execute to execute data hazards. So these happen for example, for R-type instructions, and here we've got a example bit of code that uses a subtract, an and an or. I don't know whether they're doing anything useful, doesn't really matter. It's just to illustrate what happens if we try and have 3 R-type instructions execute in sequence, and here we have a dependency on T1, and this is kind of interesting because obviously the add, the A instruction, is dependent on T1 in the next clock cycle, whereas the OR is dependent in 2 clock cycles away. There is an instruction in between, and so that's 2 interesting cases. So let's have a look to see how we proceed in time. So obviously we begin by fetching S. As S is being decoded, we fetch A, and when we're executing S, we're decoding A and we're fetching O. Now, if we're not careful, we have to stall A because S hasn't actually written its result back to the register, and we haven't been able to use that forwarding path that we introduced for load instructions. So we have to introduce a bubble, and we can allow things to proceed now because we know, due to the forwarding path that we added for loads, we can actually forward the result from the subtract to the add instruction at that point in the pipeline. Okay. Similarly, we'll be able to we'll have written the result back to the register file, so the O instruction will have actually read the correct value So there's no dependency problem at the moment. But that's only because we'd introduced a bubble in the pipeline for A. So anyway, things will then progress down the pipeline until we've finished. So the question is, how can we remove the bubble due to the dependency between the S and the A instructions? Well, we need some more forwarding. So let's look at that. Here what we're going to do is we're going to add an additional forwarding path. We're going to forward the ALU result from that pipeline register back to the execute stage. Okay, and this then extends the multiplexers that we added earlier, because we've now got two forwarding paths, one from the write back and one from the ALU forwarding, as well as receiving the values that would come in from registers or from an immediate. Okay, so let's see what the implications are of this on our pipeline. So same example, same sequence of code, subtract, add and OR, and over time, we fetch S, that proceeds to decode, we fetch A, and so on. And at this point, this is then interesting, we use our new forwarding path. So we have that new forwarding path from the memory access stage back to execute. In other words, the output of execute, or the result of execute, we can forward directly back into the input of execute, and that avoids any bubble in the pipeline. It's also interesting to think what happens in this next step. So at this point, S has reached write back. It still hasn't actually written its value to the T1 register. However, we can use our original forwarding path for load instructions to forward the result to the execute stage, so that that dependency is resolved, and so the instructions can proceed down the pipeline and everything's happy. So for arithmetic operations, using those two forwarding paths for this particular pipeline, it completely eliminates all the data hazards in the pipeline. So that's pretty cool. Let's now look at where branches are handled. So we've got these control signals and the immediate are sent from execute stage in the pipeline. Now this is obviously going to cause a bit of a hazard, because we only realise once the conditional branch reads execute whether we're going to do a branch or not. And the simple thing will be that the branch unit will have just kept basically issuing program counter values to fetch the next instruction, and as a consequence we will have an instruction being fetched and an instruction being decoded that are likely to be the instructions after the branch, and in other words they would have been fetched in error. So let's look at that in some more detail. So branches cause control flow hazards. So here's some example code. We've got a branch less than instruction, and this is basically going to branch around a bit of code that swaps the T2 and T1 registers over. Okay, and the branch conditionally branched to the label skip, which stores the T1 value at some address. Okay, so let's assume the branch is taken in this example and see what happens in the pipeline. So there again, we're going to look over time. So we're going to fetch branch. Branch is going to proceed to decode, and we're just going to do the dumb thing and fetch the instructions after the branch. Okay, so we fetch O1, now we're fetching O2. Branch gets to execute, and at this point the branch causes the branch causes the S value to be fetched on the next clock cycle, because we will have actually in execute sent the control signals and the branch offset to the branch unit So the branch unit now knows that it needs to do a branch. And so in the pipeline, we need to flush the O1 and O2 instructions from the pipeline. Okay, because they were fetched in error. And if we execute them, then we would have failed to preserve the sequential programming model. So basically, we have to clean things up one way or another. And in the abstract, we're basically sort of replacing them with bubbles in the pipeline. Also note that at this point, the branch has done its work, so logically it's proceeding down the pipeline, but it's not going to do memory access and it's not going to do write back, but still it logically proceeds down the pipeline. Okay, so in the next clock cycle, the S instruction proceeds to decode, and of course we've got those bubbles in the pipeline, and then we basically just allow that to proceed until the S is finished and whatever instructions follow it. So a few notes on branches. So in the general case, several instructions may have been fetched in error before the pipeline realizes that a branch should have happened. And for this pipeline, we'll have fetched 2 instructions in error. In a modern high-performance processor, we could easily have fetched tens of instructions before we realised that we needed to do a branch, or before we're absolutely certain we need to do a branch. To avoid breaking the sequential execution model, we need to prevent the erroneously fetched instructions from completing. So it doesn't matter actually if those erroneous instructions start working their way down the pipeline, so long as they don't update any state. Okay, that's absolutely critical. And there are a couple of approaches to this. In the previous slide, I mentioned flushing the instruction from the pipeline. So, say, mark them as invalid, which basically sort of turns them into a bubble. So that's one approach. Another approach is to add an epoch number to fetched instructions. So we sort of colour the instructions, if you like. So if we're currently executing, blue-coloured instructions, and we then come across a branch, then we tell the branch unit, we're going to move from the blue phase into, say, the yellow phase. And at this point, we also tell write back, don't just ignore any blue instructions at this point. We're now only interested in yellow instructions. And so we can allow instructions that were fetched in error to proceed down the pipeline, but they won't update any state. And that's one approach. Another approach, which I mentioned last lecture, but I'll go into just a little bit more detail, is dynamic branch prediction. And there's much more on this in Part 2 Comparative Architectures. So as I mentioned last lecture, complex pipelines tend to have basically it's much more difficult for them to execute branches early. And so we tend to have fetched a lot of instructions in error if we're not careful. So we tend to use dynamic branch prediction. And in hardware, we tend to use something like a branch prediction buffer or a branch history table. And in fact, we use this even when we're fetching the instruction. So we often want to know, even before we fetch the instruction, is it a branch? Okay, and so we will have kept that information in the history table. And the history table stores the outcome, so taken or not taken, of previous branches. And it can sort of have some sort of counter. There are all sorts of different approaches to determine whether a branch is likely to happen or not. And also, we tend to record what the branch target is. So to execute a branch, we will have checked the table, and so we'll predict what the outcome is. In fact, we even predict that it is a branch instruction, and then we start fetching from the fall through or the target that's in our predictor table. And of course, we'll still fetch the branch instruction and we'll allow it to proceed down the pipeline. And at the point when the branch instruction is actually executed properly, we know whether the branch is taken or not. And at that point, we determine whether we flush the pipeline and change the prediction bits, or whether we got it right and everything can proceed correctly. So the branch target buffer is something is part of this dynamic prediction. It's just a cache of target addresses, so we don't even need to reach instruction decode or execute to know where the branch will go. And it's just indexed by the program counter value or a hash of the program counter value in instruction fetch. Okay, and if we hit in the branch target buffer, then we can predict where the branch is likely to go. Anyway, as I said, far more details in comparative architectures. Another form of sort of branch or jump are exceptions and interrupts, in that exceptions and interrupts cause a change in the flow of control. Okay, they cause the program counter to get updated to start running different code, and typically with exceptions and interrupts, it's some sort of supervisor code. Both exceptions and interrupts are to some extent unexpected events that we want to inform, say, the operating system or runtime to deal with. Exceptions do arise sort of within the CPU, and they tend to be things like, division by zero if you've got a divide unit or an undefined opcode. But we can also have what are called software exceptions, so something like a syscall. An interrupt, on the other hand, comes from typically for some external I/O device or some sort of timer. Okay, so some external device will say, "Excuse me, I need attention, please," and the interrupt basically causes, the OS or runtime system to be invoked to basically service that I/O device or handle that timer interrupt. Dealing with these without sacrificing performance is also hard, and let's look at the issues in a little bit more detail. Firstly, handling exceptions. So in order to handle an exception, we need to save the program counter of the offending or interrupted instruction into the supervisor exception program counter register, and this is so that we can return from the exception if we're able to do so without impacting the application that's being run. We're also going to the processor saves an indication of what the problem is, so that the operating system or runtime knows what the cause is. Okay, and it's on RISC-V, it's a 32-bit value, although at the moment most of those bits are not used. So there's an exception code field. There's a couple of bits for that tell you about undefined opcodes, and 12 for hardware malfunctions and things. We then jump to a handler that's pointed to by the STVEC register, and we could have precise or imprecise exceptions. So a precise exception is one that's restartable. Okay, and this is typically slightly harder to implement, but it's often what software wants. So with a precise exception, the thing that caused the exception, which might be something like a memory fault, the pipeline tends to have to be flushed of any instructions, and the handler then executes. And then critically, at the end of the handler, we want to return to the instruction which caused the exception, and we typically execute it again. Okay. And as I said, when we talk about virtual memory in a later lecture, this, a load or a store that ends up referring to some memory that's not in our virtual address space, that will need to cause a precise exception, because we typically need to, the operating system needs to set that memory up and then restart the application. Imprecise exceptions are easier to implement and are used in some processors. Here the pipeline flushes the instructions, but you can't recover from the exception. At least you can't go back to precisely the right point. This can be used, for example, for things like illegal instruction exception. So if you just choose that if a program executes an illegal instruction, basically it's just going to call dump and you're just going to shut the application down because it's made a mistake, then you could raise an imprecise exception. Although actually most processors allow you to handle those as precise exceptions, because you might want to emulate that the instruction isn't supported by the processor. So for example, if you've got a very simple processor that doesn't support floating point, you might still want support in software. And so if you've just got an integer only processor, it could then raise an instruction exception. The operating system could then actually in software perform the floating point operation and then return to the code. So the code would run slowly, but at least it would run correctly. Now let's finish up the lecture by looking at some more advanced topics that are covered in more detail in the Part 2 Comparative Architectures course. So first of these is instruction level parallelism. So obviously we've looked at pipelining, so trying to execute multiple instructions in parallel. However, we're still fetching one instruction at a time, so it's not that parallel. Obviously, to increase instruction level parallelism, well, we could make the pipeline deeper. So we could try and do less work per pipeline stage, reduces the clock cycle. In other words, you could get a higher clock frequency. But actually, the more you do this, the more forwarding paths you have to add, the more risk there is of bubbles due to hazards. And so you do get sort of diminishing returns on that. You can also try and get more instruction level parallelism by actually fetching and issuing more than one instruction every clock cycle. So we could replicate pipeline stages. So for example, we might have a separate integer pipeline stage, we'll have a separate stage for floating point, but we might also separate integer and logical operations from memory operations. So we might have a separate memory pipe, for instance. And that would then allow us to issue multiple instructions per clock cycle. And that would give us a cycle per instruction of less than one if we do the things well. So for instance, if we had a 4 GHz processor that's four-way multiple issue, then we could get a CPI of a quarter. In other words, the instructions per clock is 4. That's assuming that we can actually find useful instructions to issue down all of these pipelines, and there are no other dependency problems or waiting on memory subsystem or anything like that. So this actually turns out to be kind of tricky. Let's look at multiple issue in a little bit more detail. As I said, more in comparative architectures in part 2. So we can have static multiple issue, and here the compiler groups instructions to be issued together and packages them into issue slots, and the compiler detects and avoids hazards. Okay, so that's one approach. It does generally mean though you're trying to do quite a lot of code optimization with knowledge of a particular pipeline that's going to implement it. Obviously, to make the life of software easier, it's a bit easier to do dynamic multiple issue, and here we basically force the hardware to examine the instruction stream and then choose instructions to issue together, and even sort of change the order of them whilst not impacting the sequential model. Okay. The compiler can still help by trying to do things like load hoisting and various other techniques to reorder instructions to make the processor's life a little easier. But nevertheless, the CPU ends up resolving all the hazards using various advanced techniques at runtime. Speculation is another exciting topic. So here we guess what to do with an instruction, or what an instruction will do once it's finished executing. And here the idea is to start an operation as soon as possible and to check whether the guess was correct, and if so, complete the operation, and if not, roll back and do the right thing. So it's common actually to both static and dynamic multiple issue, and examples include things like speculation on branch outcome, and I've already talked about branch prediction. And obviously we roll back if the branch path taken is incorrect. We can even speculate on loads and roll back if a location is updated. And there's lots of other speculative techniques used. In fact, some of the modern high-end processors, it does get kind of ridiculous. And unfortunately, it started to bite the industry. So a little bit of a side note, just something that's fairly topical at the moment. Over the last couple of years, speculation has been identified as a security risk. So there have been attacks like Spectre, Meltdown, Foreshadow, and so on. And these attacks basically rely on tricking the speculative execution mechanism to go and do something that you shouldn't be allowed to do, like going reading from some bit of privileged memory. Now, of course, the processor designers have been quite careful to ensure that even if you do speculation, you've preserved the sequential model. So why would there be a security risk? Well, the problem is that you can often, it's been demonstrated that you can do things that in speculation that, for example, cause timing behavior of the processor to change. And an example of this might be writing a value to a bit of memory and causing that memory location to be read into the cache, and then you can check the cache timing on a subsequent load, and this can actually be used to leak information. Anyway, it's actually quite an interesting topic, and if you Google for Spectre and Meltdown, you'll find a lot more details, and it's actually an area of active research in my group of how to design processors that are resistant to speculative execution attacks while still getting many of the performance benefits of speculative execution. Now, let's just look at a couple of some fallacies and pitfalls. The first one is pipelining is easy. The basic idea is fairly easy, but the devil is really in the details. We've got to detect and work around data and control hazards. Another fallacy is that pipelining is independent of technology, and that's just clearly not true. It's the actual details of the pipeline structure tend to be optimized for the particular implementation technology. And also, pipelining hasn't always been used. In the past, we haven't had nearly as many transistors to work with on a chip. And it's meant that, only more recently we've been able to use more of these advanced techniques because we have the transistor budget to be able to implement them. Also, pipeline-related instruction set architecture design needs to take account of technology trends, and there's things like predicated instructions, whether those are a good idea or not. That's kind of a subject beyond the scope of this course. Let's just talk about a few pitfalls. So poor instruction set architecture design can make pipelining really hard. So complex instruction sets, so there's old machines like the VAX, but also things that are used today. So I've talked about x86 in particular, PCs and even current iMacs all use Intel or AMD processors, and they use the x86-64 instruction set architecture, which is very complicated. It makes it very difficult to make pipelining work efficiently, and in fact Intel and AMD use what is called a micro-op approach. So they basically have a whole lot of decoding that breaks these complex instructions into simpler micro-ops to be issued down the pipeline. And the irony is these micro-ops look a lot like RISC instructions. Okay, and you might think, well, why the heck are you doing this? Why not just use a RISC instruction set to begin with? Well, of course, part of it is there's an awful lot of code written out there for the Intel architecture, and people want to be able to run that legacy code. It'll be interesting to see how things shift over the next few years, and it'll also be interesting to see Apple moving from x86 for the iMac to ARM-based processors, which are RISC-based machines, and see how well they do that transition. These complex instruction sets also usually have complex addressing modes, and that makes pipelining very difficult. And there have even been RISC instruction sets like MIPS. So MIPS actually made the delay in branches observable. So in MIPS, every instruction after a branch was always executed, regardless of whether the branch was taken or not. And that's all very well, and it made sense on a very simple pipeline, but as soon as you've got an advanced, much longer pipeline, those sort of branch delay slots, the branch delay slot changes, and yet the model presented to software is that you only have one branch delay slot, and it turns out that's a right pain to implement. So I think the general message is, you try and avoid exposing very specific pipeline details to software. Instead, it's better to just be able to give general guidance. And we talked about load hoisting, general guidance of always try and do the load as early as possible, because that will help performance on basically any machine. That's great guidance. What you don't want are things that are very subtle timing behavior, where you need specific numbers of instructions in a sequence to make things work correctly. So let's conclude. The instruction set architecture influences the design of the data path and the control logic. Data path and control also therefore influence the design of the instruction set architecture. These things go hand in hand. Pipelining improves instruction throughput using a form of parallelism. So we get more instructions completing per second, although with a very simple pipeline we're still only fetching one instruction every clock cycle, until you go to a superscalar pipeline where you try and fetch more than one. Also do remember that with pipelining, the actual latency, so the time taken to actually complete execution of one instruction, is not reduced using pipelining. If anything, it takes longer to execute a particular instruction, but due to the pipelining effect, we get much better throughput. We've talked about pipeline hazards, and in particular we've talked about data and control hazards in this lecture, and I mentioned structural hazards in the last, and we have to mitigate those to preserve the sequential programming model. And I also briefly mentioned multiple issue and dynamic scheduling to increase instruction level parallelism. However, dependencies limit the achievable parallelism and complexity of these much more sophisticated processors. Also start banging up against the power wall. You make the processor a lot more complicated, it ends up consuming a lot more power, and then you end up becoming thermally limited, and that then slows the clock frequency down. So it's a very complex design optimization space. Anyway, with that, I'll finish there. Thank you.